Artificial intelligence, AI, refers to computer systems or machines that are capable of performing tasks that typically require human intelligence, such as visual perception, speech recognition, decision-making, and language translation. The core components of AI include machine learning algorithms that can learn and improve at tasks by analyzing large amounts of data. Common techniques include supervised learning, unsupervised learning, reinforcement learning, neural networks, etc. Computer vision processing and analyzing visual data from the real world using cameras and sensors. Facial recognition, object detection, image classification are examples. Natural language processing, understanding, interpreting, and generating human language. Used for chatbots, sentiment analysis, language translation, etc. Robotics, using AI to guide robots to mimic human cognitive skills and perform tasks like assembly, delivery, surgery assistance, etc. Expert systems encode domain-specific rules to mimic decision-making and expertise of human specialists for domains like finance, medicine, engineering. Planning, scheduling, automatically developing plans and schedules by considering resources, constraints, optimization goals. Used for manufacturing, logistics, etc. Speech recognition, processing and understanding spoken languages. Used for voice assistance, real-time translation, transcribing spoken words to text, etc. AI has applications in almost every industry and field. Key benefits include automation of repetitive tasks, personalized recommendations, efficient data analysis, improved accuracy, discovering hidden insights, and freeing up humans for more creative and meaningful work. AI does have risks and potential downsides that must be carefully managed as adoption increases. Overall, AI is poised to become one of the most transformative and beneficial technologies of our time. 5G and 6G network. 5G and 6G refer to the latest generations of cellular network technology that provide faster speeds and lower latency compared to previous generations like 4G or 3G. 5G networks are starting to roll out now. Key capabilities and features of 5G include high bandwidth peak download speeds up to 20 gigabits per second, 10,100x faster than 4G. Enables new high data applications. Lower latency as low as 1 millisecond, which allows for real-time communication. Critical for autonomous vehicles. Increased connection density can support over 1 million device connections per square kilometer. Enables IoT. Ultra reliability, critical for remote surgery, industrial automation, autonomous vehicles. Network slicing, multiple logical networks can be created on top of 5G infrastructure for different purposes or clients. 6G is still in early research and development and isn't expected to be finalized until late 2020s. It aims to provide TBP speeds thousands of times faster than 5G, much lower latency, microsecond latency to enable near real-time communication, terahertz frequencies, 100x higher carrier frequency for faster communication, larger bandwidth for more data capacity, precision sensing, accurately detect motions and positioning of objects, higher security using novel cryptographic techniques. Key 6G applications may include holographic telepresence, flying autonomous vehicles, wireless brain-computer interfaces, precision industry automation, and distributed computing grids. However, the final capabilities are still to be determined as research progresses. Quantum computing. Quantum computing is a developing technology that harnesses the strange properties of quantum physics to perform calculations exponentially faster than classical computers for certain problem types. Here's an overview. Qubits, the basic unit of quantum information. Unlike binary bits, qubits can represent 1, 0, or a superposition of both states at once due to quantum phenomena. Superposition qubits can effectively be in multiple states at once. Allows quantum computers to process a vast number of potential states in parallel. Entanglement, quantum effects link qubits together such that operations on one affects the others instantaneously. Allows for parallelism. Interference, quantum wave functions can cancel out or reinforce each other, letting qubits interact and compute via interference effects. Hardware requires isolating delicate qubits and controlling them with lasers, microwaves, or electrons. Done via superconducting circuits, ion traps, quantum dots, etc. Algorithms, special algorithms like Shor's algorithm for factoring primes, demonstrate exponential speedup over classical versions. Applications, chemistry simulations, cryptanalysis, machine learning, financial modeling, and other optimization problems stand to benefit most from quantum computing. but true universal quantum computing is still a long way off due to the extreme technical challenges. Adding more qubits introduces more quantum noise and errors. The largest quantum computers today have less than 100 qubits. Thousands of logical qubits will likely be needed for them to consistently outperform classical supercomputers. Quantum computing is a promising but nascent technology. Virtual and augmented reality. Virtual reality, VR, and augmented reality, AR, are emerging technologies that create immersive digital experiences and interactions by overlaying or integrating digital content with the physical world. Virtual reality. Fully simulated virtual environments. Users wear VR headsets that display 3D visuals and play audio. Headsets track head motion, allowing users to look around and interact. Hand controllers provide input for manipulation, navigation, etc. Allows users to experience anything imaginable from game worlds to historical sites. Augmented reality. Overlays digital content onto the real-world environment. Viewed through smartphones, AR glasses, lenses, or projected over surfaces. Digital content tracks with physical objects and environments. Examples include Snapchat filters, GPS overlays, IKEA furniture visualization. Upcoming AR glasses aim to enable more seamless, interactive experiences. Key components include spatial mapping, object recognition, motion tracking sensors, and advanced optics for realistic visuals. Applications span gaming, live events, military training, engineering design, healthcare, retail, robotics, and more. VR and AR can enhance visualization, create immersive experiences, improve workflows, and provide access to remote environments. Blockchain. Blockchain is a distributed ledger technology that allows for secure, transparent record-keeping of transactions and data. Here are some key features. Decentralized blockchain networks have no central point of control. They are maintained by computers across the world adhering to the same protocols. This makes them resistant to attacks or failure at single points. Transparent transactions are recorded in permanent, public records that are transparent and verifiable to all members of the network. Provides traceability and trust. Secure transactions are cryptographically signed with private keys and recorded on blocks that are chained together securely using hashes. This makes it very difficult to alter historical transaction records. Consensus members of the network follow agreed-upon protocols to validate new transactions and blocks. This decentralized consensus protects integrity without a central party. Automated smart contracts execute automatically based on predefined conditions coded into the blockchain. Allows for complex programmable transactions. Irreversible records written to the blockchain are permanent and irreversible. Prevents double spending or tampering. Major applications include cryptocurrencies like Bitcoin, smart contracts, supply chain tracking, healthcare records, decentralized finance, and more. Challenges remain around scalability, speed, regulation, and energy usage for some blockchain implementations. But the transparency, security, and automation makes blockchain promising for the future. Autonomous vehicles. Autonomous vehicles, also known as self-driving cars or driverless cars, are vehicles that can operate and navigate without direct human input. Here is an overview of how they work. Sensors, cameras, radars, and lidars sense the vehicle's surroundings, detecting obstacles, road conditions, signs, lights, and more. Maps. Highly detailed 3D maps provide lane markings, traffic patterns, elevations, and more for route planning. Vehicles use sensor data to localize themselves on the maps. AI software. Powerful AI algorithms process all the sensor data to perceive and understand the environment. Controls driving based on traffic rules and routes. Machine learning. The AI system continuously trains and improves itself by analyzing data gathered from simulations, test drives, and actual driving experiences. Computer vision processes camera data to detect vehicles, pedestrians, read signs and signals, understand scenes and events on the road. Control systems. Actuators and autonomous driving hardware controlled by the AI to steer, accelerate, brake, signal turns, etc. Connectivity. V2X, vehicle to everything. Connectivity allows cars to communicate and coordinate with each other, infrastructure, and cloud services in real time. Redundancy. Critical components are duplicated in case of failures. Allows graceful degradation to a safe state. Autonomous driving technology promises increased safety, efficiency, and accessibility. But there are still challenges around regulation, security, testing, and driving in complex conditions that need to be overcome. Green technologies. Green technologies refer to the development and application of products, equipment, and systems that promote environmental protection and energy sustainability. Here are some examples. Renewable energy: wind, solar, hydroelectric, geothermal, and biomass power that produce electricity through renewable, low-carbon sources. Energy storage: batteries and other technologies like pumped hydro that allow renewable energy to be stored and used on demand. Critical for overcoming intermittent supply. Smart grids: modernized electrical grids that monitor energy use in real time and automatically optimize distribution for efficiency and stability as supply and demand fluctuates. Energy efficiency technologies that reduce energy consumption for buildings like green construction materials, LED lighting, smart thermostats, and passive solar heating. Electric vehicles: cars, trucks, buses, and other vehicles that run on electricity rather than fossil fuels. Reduce air pollution. Carbon capture: methods of capturing CO2 from industrial processes or directly from the air to prevent its release into the atmosphere. Waste to energy: converting non-recyclable waste into electricity, heat, or fuel through various processes. Green chemistry: developing chemicals in industrial processes that generate less waste and utilize sustainable materials and practices. Lab-grown meat: culturing animal cells to produce meat, avoiding the environmental toll of traditional livestock production. Adopting green technologies is crucial for reducing greenhouse gas emissions, slowing climate change, and building sustainable economies. Ongoing R&D aims to improve their scalability, cost-effectiveness, and worldwide adoption. Brain-computer interfaces. A brain-computer interface, BCI, is a direct communication pathway between the brain and an external device, typically a computer. BCIs allow the brain to control or communicate with the outside world without using the peripheral nervous system or muscles. Here are some key aspects. Recording sensors like electrode arrays record electrical signals from neurons in the brain. Common methods include EEG, electroencephalography, ECOG, electrocorticography, fMRI, functional magnetic resonance imaging. Decoding: signal processing and machine learning algorithms analyze and decode neural activity patterns into commands or messages. Translation: the decoded brain signals are translated into digital commands that control external devices like a computer application, speech synthesizer, robotic arm, wheelchair, etc. Feedback: external sensory stimuli like visual or touch feedback is sent back to the user to complete the control loop. Invasive versus non-invasive. Invasive BCIs like electrode arrays implanted in the brain provide higher quality signals but carry surgery risks. Non-invasive BCIs like EEG are safer but have less resolution. Applications: assistive devices for paralysis and neurodegenerative disease, controlling prosthetics, communication tools, gaming controllers, and even linking human minds to artificial intelligence. BCI technology is advancing rapidly with improvements in hardware, software, algorithms, and applications. Consumer-grade BCIs are just starting to emerge but could become a major new computing platform alongside vision and voice recognition. Internet of Things. The Internet of Things, IoT, refers to the network of physical objects embedded with sensors, software, electronics, and connectivity that enables them to collect and exchange data over the Internet. Here are some key aspects. Embedded sensors. Sensors in IoT devices can detect light, motion, temperature, location, and other data from their environment. Connectivity: wired or wireless internet connectivity allows IoT devices to send and receive data. Common protocols include Wi-Fi, Bluetooth, LTE, 5G, etc. Unique identifiers: each IoT device has a unique IP address to identify it on networks for communication. Data collection: sensor data and usage data is continuously collected by IoT devices and transmitted over networks. Analytics: collected data can be aggregated and analyzed to gather insights and enable automation. Remote monitoring: IoT devices can be monitored and controlled remotely via the Internet. Machine learning: IoT systems can be automated using machine learning algorithms to detect patterns and make smart predictions and decisions. Smart devices: examples include smart home assistant devices, health and fitness wearables, autonomous vehicles, industrial internet sensors, and many more. IoT enables objects to be controlled, accessed, and monitored remotely, which improves efficiency, accuracy, and economic benefit in many industries. Challenges include security, privacy, regulatory issues, and more. But the IoT will likely continue growing in scale and application,